Thank you.
Okay, go ahead, Daniel.
All right, thanks a lot for having me here. Indeed, I'm going to talk about the refined distance conjecture, and we're going to probe the distance conjecture in the deep interior of n=2 vector multiplet moduli. And this is based on work from 2018, together with Ralf Blumenhagen, Lorenz Schlechter, and Florian Wolf, and a paper which is hopefully appearing this month. So first, I'm going to recap some facts about the distance conjecture and the refinement that we're going to test. Then I will review how we probe the refined distance conjecture in Calabi-Yau moduli spaces using mirror symmetry. And then in the second part of the talk, I will move on to discuss hydraulic 2A duality and how the modular symmetries of the hydraulic string help us in probing the refined distance conjecture exactly. So the distance conjecture states that at infinity in moduli space, we are greeted by an infinite tower of states, which becomes exponentially light. And this statement is very strong and very weak at the same time, in a sense. So first of all, it's nice that we have this universal devastating behavior, but the decay rate alpha is a priori not specified. So we know that for a very small decay rate, the exponential looks approximately linear for a very long time. It's at first only a statement about flag directions, so moduli. And it's a statement about distance along the shortest geodesic, connecting 2 points in the moduli space and not physical trajectories. And finally, and this is the focus of today's talk, this universality may be broken at finite but large distances. So first of all, the distance conjecture presumes the existence of a non-compact direction in moduli space. And it's not directly a statement about compact directions, that is axions. But of course, we know that a related observation about axions was made very early on, even before the distance conjecture was formulated, which is that if we move into a region of moduli space where decay constants become trans-Planckian, the situation is often described by a different duality frame where the decay constants look sub-Planckian again. And now this is not really a conflict with the distance conjecture as such, but at least morally it is. If we are able to have super Planckian axion decay constants in a controlled way, we may be in trouble because we do get large axion displacements and we are not expecting a light tower of states. Of course, stronger versions of the conjecture appear in the literature, and these address these various issues from several angles. Regarding the decay rate, we expect this to be some order 1 number, determined often by some discrete parameters of our compactification. And we have lower bounds on alpha coming from several results, for example, regarding the back reaction of EFT objects like black holes or strings, by studying and scanning through string theory examples, from the trans-Planckian censorship conjecture, and also from the CFT distance conjecture. Regarding the presence of a potential, we expect that in n=1, flat directions are generically lifted, and at most we may have a residual moduli space of axions. But we may actually want some version of the distance conjecture also in this setting for Fino. And regarding the axions, these are expected to be approximately massless only in a compact domain of sub-Planckian diameter if we have a potential, so we cannot go an infinite distance in these directions. And in particular, in type 2b flux compactifications and type 2a flux compactifications, it was shown that if we try to displace an axion with a potential generated by fluxes, then after a distance of order 1 in Planck units, also the saxions receive a back reaction. So the trajectory curves into the saxions, and one is hit by an infinite tower of states. So at least in this setting where we have axions stabilized by fluxes, we have some evidence that the distance conjecture can be, in this sense, evaded for a distance of order 1 and Planck. And the interesting statement is really that in these examples, this critical distance after which we bend into these tachyons could not be tuned to be parametrically large. And more recently, also regarding the issue of fields with a potential, bounds on non-geodesicity were investigated. So this is not what we're going to talk about today. I want to introduce now the refined distance conjecture that is implicit in the original work of Oguri and Waffa and was later formulated in a precise way and investigated in examples by Bohm-Party and me and my collaborators. And this is in the current talk, we're going to talk about n equals to 2, so there will be no potential actually. And the proposed refinement of the distance conjecture is that, motivated from the axions on the last slide, it should apply to finite displacements in the following sense. For displacements which are larger than some critical distance, which is of order m Planck, there must be an infinite tower of states with exponentially decreasing mass scale. And the statement here can be made a bit more precise, and we try to do so in our paper. So the statement is we can go at most of order 1 in Planck before the exponential behavior becomes a very good approximation. And after this distance of order 1, it becomes, the approximation actually becomes exponentially good. Okay. So this, in some sense, explains the behavior of the axions modulo the fact that they are not true moduli. And it does incorporate also the highly supersymmetric case where we have the stronger statement that the exponential behavior might be exact over the whole modular space, but it makes a slightly weaker statement. So we want to probe this in Calabi-Yau moduli spaces. And in particular here, we are interested in type 2A on Calabi-Yau threefolds. And the moduli space we're looking at is the vector multiplet moduli space, which is spanned by the complexified Kläwer moduli. And the metric on this moduli space, as we very well know, is given in terms of a holomorphic prepotential. And we need this metric to compute distances on the moduli space. Now, the prepotential receives tons of corrections in n equals to 2, at least in type 2A. And in type 2A, it's hard to compute from first principles. Furthermore, the TIs are only local coordinates at the large volume point. And while we may be able to analytically continue to very small volume values of the TI, from the point of view of the large volume point, the domain of the TI is a bit unclear. Of course, mirror symmetry comes to the rescue, and we compute everything exactly in the mirror compactification of type 2B. And there we can compute the full non-perturbative prepotential, at least in principle, from the periods of the holomorphic 3 form of the mirror Calabi-Yau. Okay, so in our paper in 2018, we did this for the quintic. And for the quintic, which has H11 equals to 1, so we only have one Kläwer modulus, everything has been worked out in the past very explicitly. And we can map the type 2B complex structure moduli space, which is spanned by this single deformation psi, which lives on this cone here, can map it via the mirror map very explicitly to the type 2A moduli. And the moduli space is such that we have a large complex structure region here. Then the periods here converge until we hit the conifold singularity at psi equals to 1. And then for smaller psi, here's another special point, which we call the Landau-Ginzburg point here in the sketch on the right-hand side. So this is really the point which is the point deepest in the moduli space, so furthest from the large volume regime. And the periods and everything behaves in in a way which is, according to the distance conjecture, obviously as we approach infinity here, but the periods become polynomials. The periods have a polynomial expansion without any logarithms here in this phase. So we expect to be able to evade the distance conjecture maybe in this region. So one can then compute everything explicitly and sees, in fact, that deviations from the distance conjecture, from the asymptotics of the distance conjecture, are basically confined to this region. So we are interested in the distance from this point here to this line, basically. So this would be the critical distance that we have to travel before the exponential behavior becomes a good approximation. Now, practically, this calculation can become a bit involved. For the quintic, it's, as I told you, well known. But in principle, it's involved. You have to solve for the periods at the large complex structure point. Then you can continue. So these will be some hypergeometric functions in this case. Continue them to the small psi region, do some monodromy action here to generate a full set of periods. Then you analytically continue back, and you have to find an integral symplectic basis of periods. And then in the end, you are done and you have your metric. Now you can compute geodesics and distances on this moduli space. And the story generalizes quite straightforwardly also to other examples with h11 equals to 1. And in each case, the moduli space is a thrice punctured P1, parameterized by this psi. We have three special points. One is the large complex structure points, which is at infinite distance. We have one point which is the analog of the conifold point, and one which is here at the bottom. And these points may be at finite or infinite distance. And we are mostly interested in the case where only the large volume or large complex structure point is at infinite distance, because then we have this other phase which is of finite diameter, and we want to probe this diameter. And the phi critical from the refined distance conjecture, as I told you before, is then the maximal distance to the large volume convergence region, which is this one here. In this case, we have only one Kähler modulus, so we cannot have a vibration structure of our Calabi-Yau. So the relevant tower of states will be a KK tower for us. There will be no string. And we've studied a number of examples of hypersurfaces in weighted projective space with increasing degree. And interestingly, the critical distance, so the distance that we can travel in the small volume region in type 2a, gets smaller and smaller. So if we try to break or test this refined distance conjecture, we actually want to construct a series of geometries, maybe indexed by a discrete parameter, which goes in the other direction. So we want to have large distances in the small volume regime. So here it doesn't work. Now, geometries with more than one modulus are harder because you have more phases of the moduli space. You have always several convergence regions where some of the parameters are small and large. So you have the large volume region or large complex structure region type 2b, but then you can also send some of the complex structure parameters to 0 and discover other phases of the moduli space. So for example, in this moduli space here, we have a phase which is of finite diameter in this way, but you can go to infinite distance along this direction. Now, this was the example of the degree 12 hypersurface in P11226. And we computed geodesics and other trajectories on this moduli space and basically measured the characteristic diameters of these phases. And as you can see, these diameters are always very small. You will never find a region where you can go, let's say, 100 Planck length before you reach large volume. And more examples can be found in our paper. Okay, so that's nice, but these are just examples. Now I want to switch gears a bit and reinterpret the last result here, this picture in terms of heterotic 2A duality, and then generalize from this. So to review this, for H11 bigger than 1, our geometry may admit, sorry, this should be a strict inequality here. Our geometry may admit a K3 fibration. And in this case, the theory is expected to be dual to a heterotic string on K3 times T2. Now, one can consider then limits in which you shrink the K3 and blow up the base of the fibration such that you go to a different duality frame where the NS5 brane wrapping the shrinking K3 becomes light. So this plays the role of the heterotic string. And the aim now is to use the duality triangle 2A to be heterotic to probe the refined distance conjecture more efficiently and try to break it maybe. Okay, so we need to know something about K3 fibrations. The second cohomology lattice of K3 is this very nice one, which is a copy, 2 copies of E8 plus 3 copies of a hyperbolic lattice in 2 dimensions. And there are 2 characteristic lattices for K3 actually. One is the Néron-Severi lattice, which is isomorphic to the Picard group, and the orthogonal complement, which is the transcendental lattice. And in the context of a K3 fibration that we have here, we naturally have the notion of a lattice polarization, which means that we have devices from our Calabi-Yau, which we can restrict to the generic fiber, and they will form a sublattice of the Néron-Severi lattice. Now, in the following, we will always assume that this is such that these devices, when restricted, already generate the Néron-Severi lattice. And the row of X, I will denote the rank of it. For a row equals to 1, which is the minimal case, or the next minimal case, if you consider if you go away from the projective case, for row equals to 1, we have a Picard lattice, which is one-dimensional and is basically constrained to be generated by a single vector, which squares to 2n, where n is some integer. And these are the so-called degree 2n polarized K3 surfaces, and they have degree 2n because the generator of the Néron-Severi lattice again squares to 2n. Now, of course, if we allow for a row bigger than 2, or in our current setting, that means for type 2A on Calabi-Yaus with more Kähler moduli, then we have many more options for the K3 lattice. But if we only allow a single generator of the Picard lattice, then we're constrained to this. Okay, maybe I should note that I'm interested in this low rank of the Picard lattice because we're looking at type 2A manifolds, type 2A compactifications on manifolds with low H11. Now, let me talk a bit about heterotic F-theory duality, which we will not use much. If the K3 fiber is in addition elliptic, we can also consider the dual F-theory on the Calabi-Yau threefold times T2. But clearly this is only possible if we have a generator of the Néron-Severi group which squares to 0, which would imply that rho of X is at least 2 for us. And we don't want to consider this case for now. In principle, this would make our life more simple because we can compute in 6D, because we can just delete the torus in some sense. And we have the anomalies of 6D theories and everything, which is very constraining.
But, Daniel, one question. So why you want to restrict to low moduli? Is it because it's easier for some other reason?
Basically, I want to first reproduce this 2 moduli example and then generalize from this on. Okay, so as I told you, we want low H11 of the color BR, so we have a K3 fiber with rho equal to 1, which is not elliptic. So we lose the nice F-theory description in 6D, but in principle, we still have an 8D description in terms of F3 on K3 times K3. So that's the situation in the picture. That's what we actually studying type 2A on this color BR, which is K3 fibered. And we have the various dualities. And in the generic case, we have only the duality descending from 8D. Now, from the heterotic point of view, the 6D vacua are straightforward. We just start in 10 dimensions with E8 times E8. We choose some gauge bundle G for G on K3, satisfying this equality on the second chunk classes. We determine the gauge group as the commutant. We go to the generic point in the Coulomb branch. Then we have the spectrum of the low energy theory in 4 dimensions. In 6 dimensions. And then we can compactify on a T2, which we can now take to be arbitrarily large. And we have a heterotic vacuum, which is very nice. It's at weak coupling and large volume. What I want to call the 8D vacua can be more involved. Again, we start with E8 times E8 and 10D. And now we first compactify on the torus. And then in 8D, we can go to a locus of gauge enhancement on this torus, possibly by turning on Wilson lines. And then in the second step, we choose a gauge bundle for this gauge group G prime on K3 and proceed as above. Now, in this way, you end up with a heterotic vacuum, which can be at weak coupling, but you have possibly frozen some radii of the 2 torus in 8 dimensions. Okay, so now we connect everything. The example I showed you before, the degree 12 hypersurfaces in P11226, is actually the canonical example of heterotic type duality, type 2 duality with H11 equals to 2, as the following vibration structure. And it is supposed to be dual to the heterotic string with the T2 when we compactify to 8 dimensions at the self-dual radius, where the 2 moduli T and U are equal of the torus. So we get an SU2 gauge enhancement, and we embed instanton numbers 10, 10, and 4 into this gauge group. So this is very well known, and this example provides the stringy incarnation of Seiberg-Witten theory. And the moduli between the heterotic side and the 2A side, or the mirror 2B side, have been explicitly mapped. And at weak coupling, at weak heterotic string coupling, we match the exponential of the heterotic dilaton to this modulus phi here, basically, whereas some ratio of these 2 moduli, these 2 complex structure moduli, are matched to the J function of the heterotic T modulus of the torus. So if we just look at this slice of the moduli space, then by going over all values of psi, we basically sweep out the SL2 fundamental domain of T under the pre-image of the J function. So the moduli space on this slice here degenerates to the upper half plane modulo the SL2 transformations. And the metric on the moduli space in type 2A degenerates to the hyperbolic metric on the upper half plane. And the geodesics are just circles in the upper half plane ending on the real line. Now one can be much more explicit about this. And so I just summarized it here in a picture. So this is the type 2B moduli space, if you will. This is mirror to, at least this slice here is mirror to some 2A moduli space, which looks roughly like for the quintic, which is parameterized by some Kläwer modulus T. And under Hydraulic to A duality, this maps just to the SL2 fundamental domain. And in particular, this critical distance that we have computed, which is the diameter of this hybrid phase of the 2A geometry, where one of the Kläwer moduli shrinks to zero to a very small size, is just this arc here in the upper half plane. And of course, the metric on the upper half plane is very simple. You can trivially compute the distance along this path here, which is a geodesic. And you get an exact result, which we approximated before using a complicated mirror symmetry calculation. So from the point of view of the hydraulic string, this calculation is completely trivial, actually. Whereas in mirror symmetry, you do some perturbation in these complex structure parameters. You often don't know the closed form solutions for the periods, and so on and so on. So while mirror symmetry is in principle exact, you get a perturbative expansion practically. So the lesson is that we can compute at least some distances in this moduli space exactly using hydraulic to A duality. Now, that would be very boring if we only had this singular example. In fact, we can generalize this. The Kläwer of 3-4 that we discussed is fibered by a degree. The generic fiber is a degree 2 polarized K3 surface, but we can generalize to higher degree. So for degree 4, 6, and 8, these fibrations are very well known in the literature. There are also other Calabi-Yaos with other second Chern numbers, which also realize fibrations with these K3 fibers. And these K3 fibers are mirrored to so-called MN lattice polarized K3 surfaces, where MN is this specific lattice here. And it's known that these MN lattice polarized K3 surfaces have a moduli space, which is just isomorphic to a congruent subgroup of SL2. And the story I just discussed generalizes in the following sense. We have this congruent subgroup, and the moduli space in type 2A degenerates into a quotient of the upper half plane by this congruent subgroup in the so-called weak coupling region, where the hydraulic dilaton is large. Now, the mirror map is given by the corresponding Hauptmodul, and we can perform completely analogous computations and map everything explicitly. Just maybe a review for those of you who are not so familiar with this story. The modular group has interesting subgroups, which are defined through congruence properties of the matrix generators. And here we just consider this particular group gamma 0n, which is defined by all matrices in SL2, which have this entry equal to 0 mod n. So this looks ad hoc, but it's a nice object mathematically, which parameterizes elliptic curves, which where you specify a cyclic subgroup of order n. And this is a hyperbolic Riemann surface where you have one or several cast points and orbifold points. And you may see that this does not admit the usual T-duality transformation. T goes to -1/T, but you can consider the involutive normalizer of gamma 0n in SL2R. And this does contain the so-called Fricke involution. T goes to -1/NT. So this is a generalization of the usual T-duality in a sense. And by joining this transformation to gamma 0n, we obtain gamma 0n plus, which is of relevance in the current discussion. And the associated modular curve can be explicitly constructed as a Z2 quotient by this T-duality. Now, it may happen, and it happens in the cases that I'm studying here, that the genus of this Riemann surface is equal to 0. And this is, for example, the case if n is a prime dividing the order of the monster group, but not exclusively so. And in that case, the function field of this Riemann surface is generated by the Hauptmodul. So it's one-dimensional generated by this function. So this basically defines this function. Okay, for the 3 examples I just described, we can do this explicitly. The Hauptmodulen are well known and given in terms of theta functions and eta functions. And you see that the modular spaces, they all look very similar. It's just that, oh, maybe I should tell you that you should take the Z2 quotient along this line in order to obtain the modular space. So the lower part is folded onto the top by T-duality. The distance along the corresponding arc here can be computed. It's a trivial trigonometric integral. You get exact results. And in contrast to the 1-parameter Calabi-Yaos, we see that the distances actually do increase. And for the 3rd case on this slide, it's actually infinite. So the former finite distance point turns into an infinite distance point in this example. So in this case, we would expect that, again, the distance conjecture is, in a sense, also trivially satisfied in this non-geometric phase at the boundary here. But for the other ones, we see that we get increasing distances. So the natural thing that you want to do is to crank up n and try to break the refined distance conjecture. So if you look at higher level congruent subgroups, well, the distance along these arcs here at the bottom boundary, they do grow with n, but they only grow logarithmically. So I mean, the specifics of these, of all of these cases here are not really interesting, but you do see a growth with n. So the question then is, can we realize any n in string theory? Okay, so what about gamma 0.5 plus and beyond? Unfortunately, they don't seem to appear, or fortunately, if you want, they don't seem to appear in the same way as for n less or equal than 4. And that's because K3 surfaces of very high degree do not arise as complete intersections in toric ambient space. In fact, even for n equals to 5, which is degree 10, you need to start with a more involved construction, which is a non-complete intersection, codimension 4 in P6. So you can construct this very explicitly, but it's not as nice as the cases before. And at least I don't know a corresponding codimension 4 Calabi-Yau in weighted projective 7 that would be fibered by this. So I have not found it in the literature as well.
Daniel, another question. I'm a bit confused about one thing. So in order to test the conjecture, you need information also about the tower, right? And not just the distance.
Yes, yes.
So do you know, I mean, here you control how the possible tower of states change, or I mean, how the mass depends on n, or I don't know how, I mean, if the point becomes infinite distance, somehow the exponential behavior should appear. So the mass of the state should also change, no? So how, do you know how that correlates with the distance?
Yeah, so we probed this mostly for the 1-parameter examples. And there we looked at the KK tower, and if you naively compute the mass of the KK tower, you see that precisely in this region, which is around psi equals to 0, so in the interior of the moduli space, the exponential is not a good approximation. So you do see the deviations explicitly, and you can repeat this analysis for BPS states, and you basically get the same conclusion.
But when you change n, you just said that the finite distance point becomes an infinite distance point.
Okay,
so
yeah, no, it doesn't
tower.
become, so it's just for this particular value of n equals to 4, it becomes infinite distance. It doesn't become infinite distance for.
What is the tower there? I mean,
what is the
KK tower then should get, I mean, like somehow this should also change the behavior of the estimation of the KK mass that you did first, right? I mean, because if it becomes infinite distance, it should decay exponentially.
Yes, so, but it's a different tower, I guess. So from the hydraulic point of view, this is small volume, so you would expect winding modes. it's a different tower.
Okay.
But here you have finite distance. So from here to here, you have finite distance. You don't expect a tower necessarily.
But so one would need to estimate the mass of these winding modes to see how they behave, when you change n, right? That would be the way to do it.
Yes. So I don't really consider. So different n are different physical theories, right? In 4 dimensions, different compactifications. Yeah, so I don't have a recipe for comparing the different towers for different n.
So there's no way you can calculate the periods, the spatial geometry, because they will give you the masses, right?
Yeah, you can compute the periods. I just have not done so explicitly for all of these cases.
Okay. But yeah, that's the way you would check this one, see what the tower.
Yes, indeed. No, I did this, for example, for the quintic, and then you can see very explicitly how the masses change over the moduli space, right?
So from the heterotic side, it's how do you know these are geodesics? It's simple to see. It's simple to see.
It's just the geometry of the hyperbolic plane.
It's just very simple from that duality frame to see that it's geodesic.
Yes, indeed.
Okay.
But you can also check it explicitly using mirror symmetry. It's just a lot more involved, and it's a perturbative computation. Yeah. So you might prefer the heterotic perspective.
I mean, from the type 2, it looks like quite a hard thing to do to determine the geodesics. But from this perspective, it's much. In some sense, that's quite a nice thing about what you're doing, I guess. Yeah. Thanks.
Okay. So finally, if time permits, let me have a look. Okay, 5 minutes. Finally, I have not really told you anything about the explicit heterotic duals. So we just said, we waved our hands. Well, there must be a heterotic dual. There's a K3 surface. So there must be a heterotic dual, and the physics of this heterotic dual, that recoupling, will be governed by modular symmetries. Okay. For the explicit heterotic duals, I don't have any definite conclusions, but at least I have some suggestive compactifications of the heterotic string. So the heterotic dual for the degree 12 hypersurfaces in P11226 is again expected to rise from the specific instanton embedding for this enhanced gauge group with the SL2 factor. And this group arises at radius, so it arises in 9 dimensions actually already at radius R9 equals to 1. And this fact is reflected in the 4D compactification by the fixed point under the usual T-duality transformation T goes to -1/T, which has self-dual radius at R equals to 1 in this sense. Now for the higher level congruent subgroups, the Fricke involution has a reduced self-dual radius, which is 1/√n. Suppose now we fix in 9 dimensions of the heterotic string, we fix the radius to be 1/√n. Then T-duality acting on R8 will send T goes to -1/nt, reproducing precisely the Fricke involution, which suggests we could find the other gamma 0n plus vacua from enhanced gauge symmetries at R9 equals to 1/√n. And it's very well known that.
Sorry,
such,
can I interrupt you just for a second, just to see if I understood? So the picture here is that you don't know what is the step 2A dual, but you're just gonna try and try to find the right points in heterotic and assume there's some dual there.
So I fixed the type 2A compactification. I know it has a K3 fibration, and I know it must have some heterotic dual. The problem is that
right. So you're fixing it, and then you're going to particular values of the moduli. I see. Okay. Thanks.
Yes. So the problem, maybe to reiterate this, with these heterotic duals is that they are at weak coupling, but not at large volume. So you should describe them properly as a CFT, and it's not really heterotic on K3 times C2. It's CFT on the 2 torus fibered over K3 surface. So that's how you should think of these vacua. So they are a bit more involved.
Thanks.
Okay, so it's very well known that you can get the reduced self-dual radius from turning on Wilson lines in the Herodic string. And luckily for me, the Herodic moduli for maximal gauge enhancement in 9 dimensions have recently been classified in this nice paper. And we saw a talk in the seminar as well about this. So you can identify some candidates, which are at this point just suggestive candidates, but there is no really non-perturbative check of the duality performed here. So occurring at radii 1, so r squared 1, 1/2, 1/3, 1/4, you get these gauge groups here, and you obtain them basically by just looking at the numbers, stealing two of the Cartan generators from this factor and pushing them over to the SU factor in succession. And yes, these are the specific Wilson lines for which they arise. And actually, one can also assign instanton numbers such that at least the naively computed spectrum of vector and hypermultiplets matches the Hodge numbers of these 2A Calabi-Yau compactifications. So that's suggestive, but I have not really precisely constructed a bundle for this group over K3. Okay, actually one can see that the list continues in 9 dimensions. There's, for example, another example with r squared equals to 1/5. And we are precisely interested in the question whether we can get this number large. So yeah, the question is whether this can have any 2A dual in 4 dimensions with H11 equals to 2, and I suspect it doesn't. That brings me to my conclusions. So we have studied the refined distance conjecture using mirror symmetry and heterotic 2A duality. And using the heterotic perspective, we were able to exactly compute certain diameters in phases which are, at least in type 2A, non-trivial to calculate, because some of the Kähler moduli are of order 1. And in some limit, the moduli space degenerates into the modular curve associated to a congruence subgroup. And the diameter of the hybrid phase increases with when we crank up the level of this congruence subgroup. However, we were only able to identify explicit Calabi-Yau realizations for n less or equal 4. And at least in these cases, the diameter is always sub-Planckian. So after sub-Planckian distance, we always enter into the large volume phase. And it would be extremely interesting to identify the underlying reason for the censorship of large n. And we have seen that this is tied to the allowed gauge groups in 8 dimensions, which have also appeared in various swampy studies recently. So I think it's worth investigating this further. Thanks.
Okay. Thank you very much, Daniel. So are there questions?